Namaste children. Today we are going to learn about the combination of resistors. For some practical purposes, sometimes we need to connect more than one resistor in an electric circuit. For this purpose, we connect a number of resistors in three ways. One, series combination. Second one is parallel combination. Then, and mixed combination. Series combination of resistors is used in a circuit to increase the total resistance, whereas parallel combination is used to decrease the total resistance of a circuit. Now, before going into the combination of resistors, let us discuss once again the Ohm's law. It was stated by George Simon Ohm. It states that at constant physical conditions like temperature and pressure are kept at constant, then the amount of current flowing through a conductor is directly proportional to the potential difference across its ends. That is, I is directly proportional to V. V is equals to IR, where R is constant called resistance. According to this law, conductors are divided into two, ohmic conductors and non-ohmic conductors. Ohmic conductors are those conductors which follow Ohm's law, whereas non-ohmic conductors are those conductors which do not follow Ohm's law. If a conductor is ohmic conductor, then when you plot a graph in between V and I, it will be a straight line, whereas in non-ohmic conductors, the graph will be a curve. Now, what is resistance? Resistance is defined as the obstruction or hindrance to the flow of current. It is the ratio of potential difference to the current, that is R is equals to V by I. Its SI unit is volts per ampere or ohm. Reciprocal of resistance is called as conductance and it is designated by capital C. The SI unit of conductance is ohm inverse. Now, if the wire is thin, it will have low current and high resistance. Whereas, if the wire is thick, it will have low resistance and high current. What is affecting resistance? Resistance depends upon the length of the conductor and it is directly proportional to the length of the conductor. Therefore, R is directly proportional to L. Then resistance is inversely proportional to the cross-sectional area of the conductor. That is, R is directly proportional to 1 by A. From 1 and 2, we will get R is directly proportional to L by A. R is equals to rho L by A, where rho is called as the specific resistance of the conductor or resistivity. Specific resistance is the resistance of a conductor of unit dimensional, that is unit length and unit cross-sectional area of the conductor. That is, if length is equals to 1 meter and area is equals to 1 meter square, then R is equals to rho. It depends only on the material of the conductor and it is denoted by rho. SI unit of rho is ohm meter. Rho is directly proportional to the temperature of the conductor, also known as resistivity. Two types of resistances we can use in the circuits. One is fixed resistances, that is, their value does not change under constant physical conditions. They are set at a particular value, whereas another type of resistors are variable resistors. Their resistance can be easily changed by changing the area of cross-section and length. Combination of resistances is necessary since sometimes we need to use more than one resistor in a circuit. Then mainly there are two combinations, that is series combination and parallel combination. The third one is mixed combination of resistors will be used in the circuits. Series combination in order to increase the total resistance of the circuit, whereas parallel combination is in order to reduce the resistance in the circuit. Coming to resistors in series. When two or more resistors are connected end to end consecutively, they are said to be connected in series. According to the law of combination of resistors in series, the combined resistance of any number of resistances connected in series is equal to the sum of the individual resistances. That is, mathematically, Rs is equals to R1 plus R2 plus R3 Rn. Once again, resistance in series or resistance in series. When two or more resistors are connected end to end consecutively, they are said to be connected in series. When a number of resistors connected in series are joined to the terminal of a battery, then each resistance has a different potential difference across its ends, which depends upon the value of the resistance, but the total potential difference across all the ends of all the resistors in series is equal. When a number of resistors are connected in series, then the same current flows through each resistance. Then how can you calculate the resistance when the resistors are connected in series? The figure shows three resistors R1, R2 and R3 connected in series. Now suppose potential difference across R1 is equals to V1 and R2 is V2 and R3 is V3. Let potential difference across battery be V, then V is equals to V1 plus V2 plus V3. Applying Ohm's law to the whole circuit, V is equals to IR. Applying Ohm's law to the three resistors separately, we get V1 is equals to IR1, V2 is equals to IR2, V3 is equals to IR3. Substituting 2, 3, 4 in equation 1, IR is equals to IR1 plus IR2 plus IR3, or IR is equals to, by taking I common, R1 plus R2 plus R3. I and I gets cancelled. Rs is equals to R1 plus R2 plus R3. Therefore, we can conclude that the sum of total resistances in a series resistor connection is equal to the sum of all the resistances. So when a number of resistors connected in series are joined to the terminal of a battery, then each resistance has a different potential difference across its ends, which depends upon the value of resistance. But the total potential difference across all the ends of the resistors is in series is equal. When a number of resistors are connected in series, then the same current flows through each resistance. So resultant of resistances connected in series, once again, the figure shows three resistances R1, R2 and R3 connected in series. Now suppose potential difference across resistance R1 is V1, R2 is V2 and R3 is V3. Let potential difference across battery be V, then V is equals to V1 plus V2 plus V3. Applying Ohm's law to the whole circuit, V is equals to IR. Applying Ohm's law to the three resistors separately, we get V1 is equals to IR1, V2 is equals to IR2 and V3 is equals to IR3. Substituting 2, 3, 4 equations in equation 1, IR is equals to IR1 plus IR2 plus IR3, where IR is equals to I common R1 plus R2 R3. Therefore, Rs is equals to R1 plus R2 plus R3. Therefore, we can conclude that the sum total resistance in a series resistance connection is equal to the sum of all the resistances. Coming to resistances in parallel. When two or more resistors are connected between the same points, they are said to be connected in parallel. When a number of resistances are connected in parallel, then the potential difference across each resistance is same, which is equal to the voltage of the battery applied. Different amounts of current flows through each resistance, which depend on the value of resistance. But the current flowing through each parallel resistance taken together is equal to the current flowing in the circuit as a whole. Thus, when a number of resistances are connected in parallel, then the sum of the current flowing through all the resistances is equal to the total resistance flowing in the circuit. Then resistances in parallel is shown in the figure. The three resistances R1, R2 and R3 connected in parallel. Now, suppose current across resistance R1 is I1, R2 is I2 and R3 is I3. Let total current in the circuit be I, then I is equals to I1 plus I2 plus I3. Applying Ohm's law to the whole circuit, I is equals to V by R. Applying Ohm's law to the three resistors separately, we get I1 is equals to V by R1, I2 is equals to V by R2, I3 is equals to V by R3. Substituting 2, 3 and 4 in equation 1, we get V by R is equals to V by R1 plus V by R2 plus V by R3, or V by R is equals to V into 1 by R1 plus 1 by R2 plus 1 by R3, where V and V gets cancelled. Rp is equals to 1 by R1 plus 1 by R2 plus 1 by R3. Therefore, we conclude that the sum total resistance in a parallel resistor connection is equal to the sum of reciprocal of all the resistances connected in the circuit. Once again, the resistances in parallel. When two or more resistors are connected between the same points, they are said to be connected in parallel. According to the law of combination of resistances in parallel, the reciprocal of the combined resistance of any number of resistances connected in parallel is equal to the sum of the reciprocals of the individual resistances. That is, 1 by Rp is equals to 1 by R1 plus 1 by R2 plus 1 by R3, so on. When a number of resistances are connected in parallel, then their combined resistance is less than the smallest individual resistance. When a number of resistances are connected in parallel, then the potential difference across each resistance is same, which is equal to the voltage of the battery applied. When a number of resistances are connected in parallel or joined to the two terminals of a battery, then the different amounts of current flow through each resistance, which depend on the value of resistance. But current flowing through each parallel resistance taken together is equal to the current flowing in the circuit as a whole. Thus, when a number of resistances are connected in parallel, then the sum of current flowing through all the resistances is equal to the total current flowing in the circuit. Now, the resultant of resistances connected in parallel, as shown in the figure, three resistances R1, R2 and R3 are connected in parallel. Now, suppose current across R1 is I1, R2 is I2 and R3 is I3. Let total current in the circuit be I, then I is equals to I1 plus I2 plus I3. Applying Ohm's law to the whole circuit, I is equals to V by R. Applying Ohm's law to the three resistors separately, we get I1 is equals to V by R1, I2 is equals to V by R2, I3 is equals to V by R3. Substituting 2, 3 and 4 in equation 1, V by R is equals to V by R1 plus V by R2 plus V by R3, or V by R is equals to, taken V as common, 1 by R1 plus 1 by R2 plus 1 by R3. Getting cancelling V and V, we get 1 by Rp is equals to 1 by R1 plus 1 by R2 plus 1 by R3. Therefore, we can conclude that the sum total resistance in a parallel resistor connection is equal to the sum of reciprocal of all resistances connected in that circuit. Now, series combination versus parallel criteria are parameters equivalent resistance in series more than the highest resistor, whereas in parallel it is less than or equal to the lowest resistor. Amount of the current is less as resistance is more, whereas in parallel current is more as resistance. Switching on and off. If one appliance is switched off, other also do not work. If one appliance is switched off, others will work independently in parallel connection. Appliance failure. If one of the appliances stops working, none of the appliances will work in series combination, whereas if one appliance stops working, other will work independently. The potential difference in each appliance receives maximum potential difference in case of series, whereas potential difference is divided, so each PD receives less, each appliance receives potential difference in parallel divided, so each appliance receives less potential difference. Parallel connection, if one electrical appliance stops working due to some defect, then all other appliances keeps working normally. Whereas in series connection, when one electrical appliance stops working due to some defect, then all other appliances stop working. In parallel circuits, each electrical appliance has its own switch due to which it can be turned on or off independently. In case of series connection, all the electrical appliances have only one switch due to which they cannot be turned on or off separately. Each appliance gets same voltage in case of parallel connection as that of power source. In series circuit, the appliances do not get same voltage 220 voltage as that of the power supply line. Overall resistance in parallel connection of household circuit is reduced due to which the current supply is high, whereas in series circuit, the overall resistance of the circuit increases due to which the current from the power supply is low. Now, what are the heating effects of electric current? When electricity passes through a high resistance wire like a nichrome wire, the resistance of wire becomes very high. So, the wire becomes heated up and becomes very hot and produces heat. This is called as the heating effect of current. James Prescott Joule, he has made some observations and found the relation between current through a resistor and the heat dissipated, which is called as Joule's first law. Let an electric current I is flowing through a resistor having resistance equal to R. The potential difference through the resistor is equal to V. The charge Q flows through the circuit for time t. Thus, work done in moving the charge Q of potential difference V is equals to VQ. Since this charge Q flows through the circuit for time t, therefore, power input P to the circuit by power source is equals to VQ by T. That implies P is equals to V into Q by T. We know that electric current I is equals to Q by T. Thus, by substituting Q by I in equation 1, we get P is equals to VI. Since the electrical energy is supplied for time t, Thus, after multiplying both the sides of equation time t, we get Pt is equals to Vi into t, or Pt is equals to Vit. Thus, for steady current I, the heat produced H in time t is equals to Vit. H is equals to Vit. According to Ohm's law, we know that V is equals to IR. Therefore, by substituting V is equals to IR in the equation 4, we get H is equals to I square RT. Therefore, the heat produced in a wire is directly proportional to the square of the current and is directly proportional to the resistance of the wire and is directly proportional to the time for which current is passed. Applications of heating effect of electric current. There are many practical uses of heating effect of current. Some of the most common are as follows. An incandescent light bulb glows when the filament is heated by heating effect of current. So hot that it glows white with thermal radiation, also called black body radiation. Electric stoves and other electric heaters usually work by heating effect of current. Soldering irons and cartridge heaters are very often heated by heating effect of current. Electric fuses rely on the fact that if enough current flows, enough heat will be generated to melt the fuse wire. Electronic cigarettes usually work by heating effect of current, vaporizing propylene glycol and vegetable glycerin. Thermistors and resistance thermometers are resistors whose resistance changes when temperature changes. These are sometimes used in conjunction with heating effect of current, also called self-heating in this context. If a large current is running through the nonlinear resistor, the resistance temperature rises and therefore its resistance changes. Therefore, these components can be used in a circuit protection role similar to fuses or for feedback in circuits or for many other purposes. In general, self-heating can turn a resistor into a nonlinear and hystereotic circuit element. What is electrical energy? H is equals to I square RT according to Joule's first law gives the rate at which electrical energy is dissipated or consumed in an electric circuit. This is also termed as electric power. The power P is given by P is equals to VI or P is equals to I square R or V square by R. The SI unit of electric power is watt. It is the power consumed by a device that carries 1 ampere of current when operated at a potential difference of 1 volt. Thus, 1 watt is equals to 1 volt into 1 ampere or 1 VA. The unit watt is very small. Therefore, in actual practice, we use a much larger unit called kilowatt. It is equal to 1000 watts. Since electrical energy is the product of power and time, the unit of electric energy is therefore watt-hour. 1 watt-hour is the energy consumed when 1 watt of power is used for 1 hour. The commercial unit of electrical energy is kilowatt-hour, commonly known as unit. 1 kilowatt-hour is equals to 1000 watts into 3600 seconds, that is equals to 3.6 into 10 to the power of 6 watt seconds or 3.6 into 10 to the power of 6 joules. Once again, electrical energy and electric power. Electrical energy is the work done to maintain the flow of current in a conductor. W is equals to QV. W is equals to VIT. Wi is equals to I square RT. Since W is equals to QV, Since I is equals to Q by T and Q is equals to IT, by substituting W is equals to VIT. Then since V is equals to IR, W substituting V value, IT into IR, that is equals to W is equals to I square RT. The unit of electrical energy is joule. Coming to electric power is the rate at which electric current is used. Power is equals to work by time. P is equals to W by time. Power is equal, since W is equals to I square RT, P is equals to I square RT by T. That implies P is equals to I square R. R is equals to V by I. By substituting I square into V by I, P is equals to VI. The SI unit of power is watt. 1 watt is the power when 1 ampere of current flows across a potential difference of 1 volt. 1000 watts is equals to 1 kilowatt. 1 kilowatt hour is equals to 1000 watts into 3600 seconds, that is equals to 3.6 into 10 to the power of 6 joules. The commercial unit of power is watt hour or kilowatt hour or unit. 1 kilowatt hour is the power consumed when 1 watt of power is used for 1 hour. Once again, heating effect of electric current. If current I flows through a resistor of resistance R and T be the time for which a charge Q flows through it, then the work done to move the charge through potential difference V is equals to W is equals to VQ. P is equals to W by T, that is equals to QV by T. Our heat energy supplied is equals to P into T, that is equals to VIT. According to Ohm's law, V is equals to IR. Heat produced H is equals to I square RT.